The first images arrived on July 12, 2022, and the world held its breath. There were sweeping arcs of light bent around invisible masses of dark matter. There were galaxies colliding in slow-motion catastrophe across distances that defeat comprehension. There were curtains of gas backlit by the birth of stars, glowing in colours that Hubble never had the infrared eyes to see. For one extraordinary week, humanity looked at the universe through the sharpest telescope ever built, and the universe looked back. And then, almost immediately, something was wrong. Not wrong as in broken, not wrong as in disappointing. Wrong as in, something kept appearing in the images that had no right to be there. Tiny, compact, persistently, defiantly, hauntingly red. They were not galaxies in any form astronomers recognized. They were not stars. They were not artifacts. They appeared in every single field the telescope observed, dozens of them per image, and then hundreds, and eventually thousands, scattered across the infant universe like embers blown from a fire no one had yet found. Astronomers named them the little red dots, and for 3 years they could not explain them, not even close. To understand why the little red dots matter so profoundly, you first need to understand what it took to see them. The James Webb Space Telescope did not happen quickly, it did not happen cheaply, and it did not happen without the kind of institutional patience that borders on geological. The telescope's origins trace back to a 1989 report by the Space Telescope Science Institute, a document that described, in essentially theoretical terms, the kind of observatory that would eventually succeed Hubble. A large, cold, infrared-capable mirror positioned far from Earth, capable of seeing light that originated in the first few 100 million years after the Big Bang. From that 1989 report to December 25, 2021. The date of launch was 32 years. The total cost reached $10 billion, making it the most expensive science instrument ever built. The primary mirror, composed of 18 hexagonal gold-coated beryllium segments, spans 6.5 meters from edge to edge. Hubble's mirror is 2.4 meters. That difference in diameter translates into a light-gathering area roughly 6.25 times larger. But the transformative capability of JWST is not its size alone. It is its position, its temperature, and its eyes. Hubble orbits Earth at approximately 547 kilometers altitude, in a region of space warm enough for ambient infrared interference to cloud its instruments. JWST orbits the Sun at what astronomers call the second Lagrange point, L2, a gravitational equilibrium 1.5 million kilometers from Earth in the direction away from the Sun. At that location, shielded from solar radiation by a 5-layer sunshield, the size of a tennis court, the telescope's instruments cool to a temperature of approximately 233 degrees Celsius below zero. At that temperature, thermal noise from the telescope itself drops to near zero, and the instruments can detect the faint infrared whisper of light that left its source more than 13 billion years ago. That is what JWST was built to do. See the first light, witness the first galaxies, watch the universe ignite from darkness. What no one expected was that the first thing to genuinely confound them would not be a galaxy too old, or a star too large, or a black hole too massive, but a population of tiny, persistently red, completely unclassifiable objects that appeared in every single image the telescope took, hundreds of millions of light years into the past, demanding an explanation that the entire theoretical framework of modern cosmology initially could not provide. That is where the story truly begins, and it begins with a colour and a question and a silence that lasted the better part of 3 years. The first clue was the colour. Red in astronomy is never accidental. It is always information. When light travels across the expanding universe, the fabric of space itself stretches the wavelength of that light, pushing it from blue toward red and eventually into the infrared, a process called cosmological redshift. The further an object is, the more its light has been stretched, and the redder it appears to instruments like JWST's near-infrared camera, known as NIRCam. So when early analyses of JWST's first data revealed a population of compact, red objects scattered across fields containing galaxies from the universe's first billion years, The initial assumption was that these were simply old, distant galaxies, far enough away for their light to have been heavily redshifted into the red end of the spectrum. But the redness of the little red dots was not purely cosmological. It was intrinsic. The objects were red at their source. When astronomers applied spectroscopic analysis, separating the light of individual dots into its constituent wavelengths, building what astronomers call a spectral energy distribution, the results were peculiar in a way that went beyond cosmological distance alone. The dots appeared blue in ultraviolet wavelengths and dramatically red in the optical part of the spectrum, producing what analysts described as a characteristic V-shape in their spectral signature. Blue at one end, a sharp dip, then a surge back to red. That shape, known technically as a Balmer break, named after the Swiss physicist Johann Balmer, whose 1885 equations describe the discrete energy transitions of hydrogen electrons, is a fingerprint. It is left by hydrogen absorbing specific wavelengths of energetic light. And in a galaxy it usually means one thing: the object is full of young, hot, energetic stars. By March 2024, a landmark paper led by Jorrit Matthey of the Institute of Science and Technology Austria, published in the Astrophysical Journal, formally named the objects and catalogued them at scale. The paper, drawing on data from the EAGER and FRESCO JWST survey programs, confirmed that these little red dots were real, numerous and deeply puzzling. Their number density, how many of them existed per unit volume of space in the early universe, was roughly 10 times higher than existing models predicted for any known category of early object. 10 times, and 80% of the objects studied showed broad Balmer emission lines in their spectra, the kind of broad, smeared outlines that, in every other context astronomers had encountered, indicated a single unambiguous cause: gas moving at hundreds of kilometers per second under the gravitational pull of a supermassive black hole. This is where the first paradox emerged. Call it the size paradox. If the little red dots were galaxies full of young, hot stars, the natural explanation for a strong Balmer break, then they would need to contain tens of billions of solar masses worth of stellar material. But the dots were unambiguously tiny. Detailed morphological analysis placed their effective radii at no more than 500 light-years, and many measured below 150 light-years. For context, the Milky Way stretches approximately 100,000 light-years from edge to edge. These objects were at most 0.5% of that diameter. Fitting tens of billions of stars into that volume would require packing stellar material at densities that would make the night sky of any planet within such a galaxy so bright that the concept of darkness would have no meaning, and that, under the known physics of stellar formation and interaction, was essentially impossible. And if they were not galaxies, but instead active galactic nuclei, the blazing accretion disks of actively feeding supermassive black holes, which also produce broad emission lines in their spectra, then a second problem emerged immediately. Active galactic nuclei glow in X-rays. They glow intensely, consistently, measurably in X-rays. When material falls toward a supermassive black hole and heats to millions of degrees in the swirling accretion disk, it produces X-ray radiation at rates that no other astrophysical process can mimic. It is their calling card, their fingerprint, the one signal that separates active galactic nuclei from every other bright object in the universe. The little red dots showed no X-ray emission, none. Not faint, not suppressed, not marginal. The X-ray sky, where known active galactic nuclei blazed like beacons, was silent at the positions of every little red dot astronomers pointed their instruments toward. 3 separate stacking analyses, in which researchers combined the X-ray data at hundreds of LRD positions to pull any faint signal from the noise, returned results consistent with zero, no X-rays, no dust signature, no variability, broad emission lines, enormous apparent mass, absurd compactness, which raises a question that kept cosmologists awake through the better part of 3 years. If they are not galaxies, and they are not ordinary black holes, then what in the name of the observable universe are they? Before the identity question could be answered, it had to be fully understood. and fully understanding it required confronting what the little red dots were doing to the standard model. Not the standard model of particle physics, but the LCDM model, the lambda cold dark matter paradigm, the cosmological framework that describes how the universe grew from the plasma of the Big Bang into the structured web of galaxies and filaments and voids we observe today. LCDM is not a simple theory. It is one of the most observationally tested frameworks in the history of science, built over decades from measurements of the cosmic microwave background radiation, the large-scale structure of galaxy surveys, the expansion rate of the universe, and the demographics of galaxy populations across billions of years of cosmic time. It is the model that tells astronomers when galaxies should form, how massive they can be at a given cosmic age, how quickly black holes can grow, and how the universe's structures should look at the epoch of reionization. The period between roughly 380 million and 1 billion years after the Big Bang, when the first stars and galaxies ionized the neutral hydrogen that filled the universe. Under LCDM, building a massive galaxy takes time. Dark matter halos must collapse. Gas must cool within those halos. Stars must ignite, live, die, seed subsequent generations of star formation, with the metals they synthesize in their cores. The process is inexorable, physically constrained and sequential. A galaxy the mass of the Milky Way cannot exist 500 million years after the Big Bang under LCDM. Not because anyone decided it shouldn't, but because the physics of cooling, accretion, and star formation set a hard speed limit on how quickly mass can be assembled. The problem was that the little red dots, if they were interpreted as massive galaxies, appeared to be vastly violating that speed limit. A team including Joel Lager at Pennsylvania State University and Ivo Labbe at Swinburne University, working with the first JWST deep field data from the UN Cover Survey in 2022, identified a set of these compact red sources and, using their apparent brightness and spectral properties, estimated their stellar masses. The estimates were staggering. One candidate appeared to contain as much stellar mass as our entire Milky Way, perhaps more, in a universe less than 700 million years old. Lager's team, struggling for a term that conveyed the appropriate sense of shock, called them universe breakers. The informal description spread with the speed of a preprint. If these objects were genuinely what they appeared to be, massive, mature galaxies in an infant universe, then either the James Webb Space Telescope was misreading the data, or the LCDM model was wrong in a fundamental way. Call this the abundance catastrophe. In the LCDM framework, the number density of massive galaxies in the universe's first billion years should be vanishingly small. The model predicts perhaps a handful across the volumes of sky that JWST was surveying. The observed number density of the little red dots was between 10 and 100 times higher. If each of those dots represented a genuinely massive galaxy, the implied excess of stellar mass in the early universe would require either a star formation efficiency of essentially 100%, meaning every atom of gas that entered a dark matter halo turned immediately into a star with no waste, no feedback, no regulation, a physical impossibility, or the cosmological model describing the assembly of matter after the Big Bang was wrong in a way that 3 decades of precise observation had somehow missed. There was a third option, of course, and this is where the science grew genuinely subtle. The third option was that the mass estimates themselves were wrong, not because the data was bad, but because the models being used to interpret the data were being applied in a regime they had never been designed for. Mass estimates for distant galaxies are derived by fitting the observed spectral energy distribution, the shape of the light across wavelengths, against libraries of simulated galaxy spectra. Those libraries are built from stellar population models that assume entirely reasonably that the light from a galaxy is dominated by its stars. But what if some of these objects were not dominated by their stars? What if the dominant source of light was not stellar at all? The V-shaped Balmer break that characterized the little red dots was peculiar in ways that went beyond a simple starburst. A genuine Balmer break in a galaxy is produced when the light of hot young stars is partially absorbed by cooler hydrogen in the surrounding medium. But the break in the LRDs was sharper than any stellar population model could produce. Sharper by a margin that stellar physics, however extreme, could not bridge. And while 80% of the objects with spectroscopic data showed the broad Balmer emission lines consistent with rapidly moving gas moving at velocities between 900 and 4 zeros in kilometers per second in some cases, they also showed something unusual in the fine structure of those lines. The lines were broad, yes, but their cores were narrow, impossibly narrow if the broadening came from the actual bulk motion of gas around a black hole. Narrow in a way that pointed to a completely different mechanism of line broadening altogether. This was, to my mind, the single most important observational clue in the entire puzzle, and it took 2 years and some of the highest quality JWST spectra ever obtained to recognise it for what it was. The narrow core of a spectrally broad emission line is the signature of electron scattering. When photons travel through an extremely dense, hot plasma of free electrons, a medium so dense that the electrons themselves scatter the photons multiple times before they escape. The resulting emission line is broadened statistically, not dynamically. The photons are not being produced by gas moving at 4,000 kilometers per second. They are being scattered into a broad profile by the sheer density of the ionized medium surrounding their source, and the narrow intrinsic core of the line, the true unscattered signal buried beneath the scattered envelope, reveals the actual velocity of the emitting gas, which was not thousands of kilometers per second. In most LRDs, the intrinsic line width implied a black hole mass of somewhere between 100,000 and 10 million solar masses. This is where the size paradox collapsed in a direction no one had anticipated. The little red dots were not harbouring black holes 1 billion times the mass of the Sun, as initial mass estimates implied. They were harbouring black holes 100 to 1,000 times less massive than that. They were, in the language of Vadim Rusakov and Darach Watson's landmark 2026 Nature paper, the lowest mass black holes known at high redshift. Not the monsters of the early universe, not the universe breakers, the infants, but if the black holes were that small, something else had to account for the enormous luminosity of these objects. The sheer brightness that had made astronomers think they were looking at billions of stars, and that something else, it turned out, was stranger and more beautiful than anyone had predicted. To understand what the little red dots actually are, it helps to understand what happens when a black hole eats with extraordinary, almost physically illegal enthusiasm. Every black hole has a natural limit on how quickly it can accrete or consume surrounding material. That limit is called the Eddington luminosity, named for the British astrophysicist Arthur Eddington, who derived it in 1916. As material falls toward a black hole and heats in the accretion disk, it radiates energy, light, X-rays, gamma rays, and that radiation pushes outward on the surrounding gas, exerting radiation pressure. When the rate of accretion becomes high enough that the outward radiation pressure balances the inward gravitational pull on infalling material, you reach the Eddington limit. Push beyond it, and the radiation blows the infalling gas back out faster than gravity can pull it in theory bringing accretion to a halt. The little red dots appear to be accreting at or near the Eddington limit, but they are doing so inside a cocoon of ionized gas so dense, so compact, and so optically thick that it fundamentally alters what we observe. The key finding from the Copenhagen team, led by Vadim Rusakov and Professor Darach Watson of the Niels Bohr Institute's Cosmic Dawn Center, whose paper was accepted by Nature in early 2025 and published in the journal's January 14, 2026 issue, came from an extraordinarily detailed analysis of the highest quality spectra obtained by JWST on a sample of objects with confirmed LRD characteristics. Their critical discovery was the electron scattering signature discussed in the previous chapter. Broad emission lines with narrow intrinsic cores, consistent not with bulk gas motion, but with photon scattering through a dense, ionized plasma. What the data required, when the electron scattering model was fitted carefully to the observations, was a cocoon of ionized gas, with an electron density high enough to scatter photons multiple times before they escape. The implied sizes of these cocoons were measured not in light years, but in light days, regions of space spanning perhaps 10 million kilometers in diameter. A black hole of between 100,000 and 10 million solar masses, accreting at close to the Eddington rate, surrounded by a shell of ionized gas so dense that it reprocesses virtually every photon the accretion disk produces before releasing it into the universe. That reprocessing is everything. The accretion disk of a black hole, under normal circumstances, produces copious X-ray radiation, hard photons generated by the extreme temperatures of infalling material. But in the dense ionized cocoon, those X-rays are absorbed by the gas and re-emitted as lower energy, optical and near-infrared photons. The cocoon converts the black hole's blazing X-ray emission into red light. It converts the fingerprint that astronomers use to identify black holes into the one wavelength range that JWST is most sensitive to, and it does so completely, suppressing X-ray emission to the point of undetectability while flooding the telescope with exactly the red, optically bright, spectrally peculiar signature that made the little red dots so baffling. The weak X-ray emission was not evidence against a black hole. It was evidence for a cocoon so thick that the X-rays never escaped. The flat or declining infrared spectrum, another anomaly that had puzzled researchers, was also explained by the cocoon model. Normal dust-reddened active galactic nuclei show a steeply rising infrared spectrum because the dust itself, heated by the embedded source, glows in the mid-infrared. The LRDs showed no strong thermal dust signature. The Copenhagen model explains this because the gas cocoon, unlike dust, does not have a strong thermal emission peak. It absorbs and re-emits through a different physical mechanism, nebular emission from the ionized gas itself, producing a flatter spectral energy distribution without the characteristic infrared rise of a dusty torus. The weak variability, yet another anomaly, was explained by the same physics. Black holes surrounded by normal dust structures show wild luminosity fluctuations as the accretion rate varies, but a dense gas cocoon acts as a smoothing layer. Fluctuations in the underlying accretion are averaged out, their variability signal diluted by the time the rate-assessed photons escape the cocoon. The LRDs do not vary much because they are seen through a buffer that blurs sharp changes into smooth constancy. What the Copenhagen team had done, and this is the part that I find genuinely staggering, was to show that a single physical model, with parameters entirely consistent with known physics, explained simultaneously the red colour, the V-shaped Balmer break, the broad emission lines, the narrow line cores, the absence of X-rays, the absence of hot dust, the absence of variability, and the apparent compactness, every single anomaly, simultaneously, not by invoking exotic new physics, but by working out with extraordinary mathematical care what a perfectly ordinary black hole looks like when it is this young, this small, and this thoroughly buried in its own birth cocoon. But as satisfying as the Copenhagen answer was, and it was deeply, beautifully satisfying, it shared the stage with another theory that was arriving from a different direction entirely, and raising a possibility even more extraordinary. What if at least some of the little red dots were not black holes inside cocoons of gas? What if they were something that no one alive had ever seen before, something theorists had dreamed about in equations for 20 years, something that should exist at the cosmic dawn but had never, until JWST, been observable? What if they were black hole stars? In the summer of 2022, Rohan Naidu was a postdoctoral fellow at the Massachusetts Institute of Technology, embedded in the astrophysics group of Professor Anna Christina Eilers, and doing what postdoctoral fellows do, managing an active research portfolio, moving carefully between projects, building the kind of slow, methodical momentum that academic careers are made of. He was 28 years old. Then JWST turned on. Naidu was in the group that received early access to the telescope's first data, and within days of the initial public release in July 2022, he was already noticing the dots. They were everywhere, not once, not in a single field, not as an anomaly, everywhere. In every deep exposure the telescope took, scattered among the familiar arcs and spirals and star-forming regions of the deep universe. There were these tiny, compact, violently red objects that did not resolve into galaxies, did not match any known template, and declined to disappear when inspected more closely. He did not immediately drop everything. First several months of analysis were cautious, collaborative, dispersed across teams working in parallel. Confirmations came slowly, but by mid-2023, a spectroscopic follow-up from the UN cover program and the early Rubies observations began to reveal just how peculiar the LRD's spectra were. The V-shaped breaks, the broad lines, the X-ray silence. Naidu made a decision that by his own account was not entirely rational. He set aside his other projects, all of them. He told colleagues and collaborators that the little red dots were, in his words, definitely, by far, the most exciting thing to come out of JWST, and that he was fully working on this and setting everything else aside. In the hyper-competitive, publication rate conscious world of academic astrophysics, that is not a minor declaration. It is a stake driven into the ground. What drew him so completely was not one thing but an accumulation of anomalies that felt, to his mathematical intuition, like they were pointing at a single, unified explanation he could not yet see. The V-shaped spectrum, the compactness, the fact that the objects appeared densely in the universe's first billion years, and then, abruptly, completely, with the finality of a theatrical curtain, disappeared by approximately 1.5 billion years after the Big Bang. Not faded, not evolved, gone. No analogues at lower redshift, no gradual transition. A population that blazed in the cosmic dawn and then vanished as though it had served its purpose and ceased to exist. That disappearance was, for Naidu, the deepest clue. A population of objects that exists only in a narrow cosmic window, between roughly 600 million and 1.5 billion years after the Big Bang, is telling you something about a phase of cosmic evolution. Not an object type that persists, evolves, and grows old alongside the universe. A phase, a stage, a chrysalis. His collaboration with Anna de Graaf of the Max Planck Institute for Astronomy at Heidelberg began in earnest around the time of the Rubies survey, the Red Unknowns, bright infrared extragalactic survey that de Graaf had proposed to the Space Telescope Science Institute in early 2023, requesting nearly 60 hours of JWST time to obtain spectra of approximately 4,500 red, distant objects identified in two major JWST deep fields. The proposal was approved, the observations began, and in July 2024, while working through the Ruby spectra, de Graaf's team encountered the object they would call the Cliff Rubies UDS 154183, is a little red dot at redshift 3.5, meaning its light was emitted approximately 11.9 billion years ago, when the universe was roughly 9 billion years old. By LRD standards, it sits at the lower edge of the characteristic redshift range, and yet it had the most extreme Balmer break of any object in the Rubies sample. A cliff edge drop in emission below the Balmer limit so sharp, so precipitous, so unlike anything any stellar population model could produce, that when de Graaf first examined the spectrum, she described it to colleagues as forcing them to go back to the drawing board entirely. The Cliff spectrum had essentially zero ultraviolet emission, and then a sudden, violent spike at longer, less energetic wavelengths. A transition so sharp that it implied not just a population of young stars, but something generating that break through a purely non-stellar mechanism. The gas producing the Cliff spectrum was cold. The light was dominated not by blazing blue stellar photons, but by the cooler, longer wavelength emission of hydrogen in its lower energy states, a signature more like the atmosphere of a cool, low-mass star than anything associated with an active galactic nucleus or a star-forming galaxy. When Naidu and de Graaf began working through the models together, the one that fit the Cliff, and subsequently several other Rubies objects, was radical. It required a structure that combined elements of both a black hole and a star without being cleanly either. A supermassive black hole, accreting at super Eddington or near Eddington rates, but embedded not in a thin accretion disk surrounded by a dust torus, as in normal active galactic nuclei, but inside a spherical envelope of gas so massive, so opaque, and so thermally dominated by the black hole's energy input that the entire system, black hole plus gas envelope, behaved optically like a single, cool, extended stellar atmosphere. The black hole provided the energy. The gas envelope provided the photosphere. From the outside, it looked like a cold star. From the inside, it was a feeding cosmic engine. They called it a black hole star. The term had been predicted. In 2006, Mitchell Bagelman of the University of Colorado Boulder had published a theoretical paper describing what he called quasi-stars, enormous gas clouds in the early universe that collapsed into temporary stellar configurations, burning briefly through nuclear fusion before their cores imploded into black holes. But Bagelman's key insight, one he admits surprised him when he worked through the mathematics, was that the collapse would not release enough energy to blow the gas envelope away. The black hole would form inside the star, take over from nuclear fusion as the energy source, and the system, enormous gas envelope sustained from the inside by a black hole's accretion luminosity, would persist for millions of years. He published this prediction in 2006 and watched it sit in the literature, a theoretical curiosity with no observational counterpart, for the better part of 2 decades. Then JWST found the little red dots when Naidu and de Graaf's team submitted their paper formally identifying the cliff as a black hole star candidate, alongside a companion theoretical paper by Naidu, de Graaf and collaborators including astronomer Rohan Naidu's Ruby's team, published in July 2025. Bagelman described his reaction in terms of quiet vindication. "I had been thinking about this for almost 20 years, he said, to see something that looks like what I predicted. It's one of those moments in science that you don't expect to actually arrive." But Naidu was not done. The question that consumed him after the cliff was the broader one. If the cliff was a black hole star, what was the destiny of these objects? They appeared in the cosmic dawn. They disappeared 1.5 billion years after the Big Bang. Black hole stars, according to Bagelman's original models, should shed their gas envelopes over timescales of millions to tens of millions of years, as the black hole grows massive enough to drive powerful outflows. What they leave behind, once the envelope is gone, is a naked, moderately massive black hole, a black hole that has spent its infancy growing at near Eddington rates inside a protective gas cocoon and emerges into the universe already equipped to continue growing toward the billion solar mass scales we observe in the quasars and active galactic nuclei of a slightly later epoch. The little red dots, under this interpretation, are the missing chapter. The baby pictures of the supermassive black holes that sit at the centre of every large galaxy in the modern universe. The phase that Lee CDM always needed to explain how those monsters got so big so fast, but that the universe had hidden from every telescope built before JWST because their light was trapped in the one wavelength range that only JWST could see. For Naidu, that realization that these tiny, crimson, inexplicable objects were potentially the birth events of every supermassive black hole that has ever existed, was the moment he put the paper down and sat with it. He has said as much in public presentations, in interviews, in seminars at the Space Telescope Science Institute, where he laid out the black hole star model to an audience of cosmologists who, by his account, leaned forward in their seats rather than backward. This is, at its core, not simply a discovery about objects at a redshift of 5. It is a discovery about origins, about where the engines at the hearts of galaxies came from, about whether the universe's most powerful forces had a childhood, and whether JWST has just found the photographs. Understanding why the discovery of the little red dots carries civilization-level weight requires understanding the problem they solve, and how deep that problem actually runs. In every large galaxy we have ever studied, the Milky Way, Andromeda, the ellipticals and spirals and irregular galaxies that populate the local group and the distant clusters, there is a supermassive black hole at the centre. Not in some of them, not in most of them, in all of them, without exception, above a certain galaxy mass threshold. The Milky Way's central black hole, Sagittarius A star, weighs 4.154 million solar masses. Andromeda's is heavier, approximately 100 million solar masses. The most massive central black holes measured in nearby galaxies exceed 40 billion solar masses, concentrated at a single point in space, surrounded by a galaxy whose entire stellar mass they outweigh by a factor of thousands. Supermassive black holes did not cause much theoretical anxiety, as long as astronomers assumed they formed at the same rate galaxies did. That dark matter halos collapsed, galaxies grew, central black holes accumulated mass slowly over billions of years through mergers and steady accretion, and the behemoths we see today are the product of 13.8 billion years of gradual gravitational dining. That assumption was comfortable. It was consistent with Lee CDM. It required no exotic physics. JWST broke it. Beginning in 2022 and accelerating through 2023 and 2024, JWST spectroscopy began confirming the existence of actively accreting supermassive black holes at redshifts above 7, meaning in a universe less than 800 million years old. These were not small black holes. A confirmed active galactic nucleus at redshift 7.04, identified in the Abell 2744 cluster field and designated Abell 2744 QS01, hosted a black hole massive enough to be described by its discoverers as a naked black hole, one that appeared to have more mass than the stars surrounding it, suggesting it had grown to supermassive scales before its host galaxy could catch up. The object Kappa's LRDZ9, confirmed in 2025 as the highest redshift active galactic nucleus yet identified at redshift 9.288, had a black hole accreting in a universe roughly 540 million years old. 540 million years. The universe's entire lifespan at that point was less than 4% of its current age, and inside it, a black hole was already eating at rates consistent with masses that would eventually reach hundreds of millions or billions of solar masses. This is the mass paradox of the early universe, and it has two sharp edges. The first is the growth rate problem. Black holes cannot grow arbitrarily fast. The Eddington limit sets a natural maximum accretion rate, and even at that maximum, a black hole starting from the remnant of a typical stellar explosion, a stellar mass black hole of perhaps 10 to 100 solar masses, takes approximately 700 million years to reach 1 billion solar masses. That is barely achievable in the time available, even if accretion were perfectly continuous and perfectly efficient, which it is not. The second edge is the seed problem. Where do the initial black holes, the seeds, come from? If they form from dying stars, their starting masses are too small and the growth timescale is impossibly tight. The universe would need to have started growing supermassive black holes before the first generation of stars even completed their lives. Something is wrong with the picture. The little red dots address both edges simultaneously. If LRDs are young black holes accreting at or near the Eddington limit inside dense gas cocoons, as the Copenhagen team's Nature paper argues, then their masses of between 100, 0s and 10 million solar masses represent an intermediate seed population that has already bypassed the stellar death formation pathway entirely. These are not the children of dying stars, they are something else, and the leading candidate for what they are leads to one of the most theoretically provocative concepts in modern cosmology. The direct collapse black hole, under the direct collapse model, proposed in various forms since the early 2000s, and refined through work by researchers including Muhammad Latif and Kohei Inayoshi among many others. A black hole forms not from the death of a star but from the sudden, catastrophic gravitational collapse of an entire cloud of primordial gas. In the right conditions, regions of the early universe where hydrogen cooling is suppressed by strong ultraviolet radiation, preventing the gas from fragmenting into stars, a massive gas cloud can collapse without first passing through a stellar phase. The collapse produces a direct collapse black hole with an initial mass of approximately 100, 0s to 1 million solar masses. Not 10 solar masses, not 100, 1 million. A seed massive enough that subsequent Eddington rate accretion can plausibly produce billion solar mass supermassive black holes within the first billion years of cosmic time, the little red dots. With their measured masses of 100,000 to 10 million solar masses, their Eddington rate accretion signatures, and their dense gas cocoons that both fuel the accretion and explain the peculiar spectral properties, fit the direct collapse black hole formation scenario with a precision that is, at the very least, suggestive. Fabio Picucci of the Harvard Center for Astrophysics, who has spent years modelling the demographics of high redshift black holes, has argued in a series of papers that the LRD population's number density, mass distribution, and redshift range are consistent with a population of direct collapse black holes that have recently begun accreting from their surrounding gas halos. Picucci's group added a further layer in mid-2025 with a paper linking LRD formation to the spin of the dark matter halos in which they reside. Dark matter halos, the vast, invisible gravitational scaffolding inside which all galaxies form, rotate, and the rate at which they spin influences how compact the galaxy or black hole system that forms within them turns out to be. Picucci and colleagues argued that little red dots preferentially form in slowly spinning dark matter halos because low angular momentum in the halo means infalling gas does not dissipate into a wide, rotationally supported disk, but instead collapses more directly toward the centre, exactly the conditions needed to avoid fragmenting into stars, and instead feed a direct collapse black hole formation event. But the most striking piece of observational evidence for the LRDs as a pivot point in cosmic evolution came not from a mass measurement or a spectral model, but from a galaxy that went by the name Virgil, observed by JWST's mid-infrared instrument roughly 800 million years after the Big Bang. Virgil appeared, in visible and ultraviolet light, to be an ordinary enough early galaxy, compact, somewhat blue, actively forming stars. But MIRI's longer wavelength view revealed a mid-infrared excess consistent with the presence of a heavily obscured active galactic nucleus, a dust-shrouded black hole far more massive than the galaxy surrounding it. The stellar mass of Virgil's host was modest. The implied black hole mass was not. The ratio of black hole mass to stellar mass was inverted compared to every modern galaxy ever measured. In the Milky Way, the central black hole is roughly 1/1000% of the total stellar mass. In Virgil, the black hole appeared to rival or exceed the surrounding stellar population. This single measurement, reported by Pierluigi Rinaldi's team from the Space Telescope Science Institute in late 2024, reframed a question that cosmologists had considered essentially settled. Which came first, the galaxy or the black hole? For decades, the default assumption was galaxies first, black holes second. Stars form in dark matter halos, galaxies grow, central black holes eventually accumulate. Virgil suggested the opposite. The black hole grew first. The galaxy was in some sense still in the process of building itself around a black hole that had already reached near final mass. If this pattern holds, if Virgil represents a general feature of the LRD population rather than a curiosity, then the standard narrative of galaxy formation is not just incomplete. The causal arrow runs the wrong way. Supermassive black holes do not wait for galaxies to assemble around them. In the universe's first billion years, at least in some cases, perhaps in many cases, perhaps in most cases, the black hole assembles first. The galaxy follows. That is not a minor revision. That is a conceptual inversion of a framework built over 40 years of observational cosmology. And the little red dots, those tiny crimson, seemingly innocuous specks that JWST found in every single image it took, are the objects forcing that revision. There was one more piece of the escalation still to come, though, and this one touched not just the history of galaxies, but the physics of the moment the universe itself became transparent. The epoch of reionization, the event that determined the conditions in which every star, every planet, and every atom of complex chemistry in the observable universe would eventually form. The little red dots might have lit the universe, or rather, they might have been doing so for the entire time we were looking, and we had no idea, because their light came in precisely the colour our telescopes could not see. Cosmic reionization describes the transition, between roughly 380 million and 900 million years after the Big Bang, during which the neutral hydrogen that pervaded the universe was broken apart, ionized, by the first intense sources of ultraviolet radiation. Before reionization, the universe was opaque to ultraviolet light, filled with a fog of neutral hydrogen that absorbed any energetic photon attempting to travel through it. After reionization, that fog cleared, and the universe became the transparent medium through which we now observe distant galaxies. Understanding what drove reionization is one of the central problems in observational cosmology. The standard answer for decades was simple: young, hot stars. The first generation of stellar objects, forming in the first dwarf galaxies of the cosmic dawn, produced enormous amounts of ultraviolet radiation that slowly, ionization bubble by ionization bubble, chewed through the neutral hydrogen fog. This model is elegant, physically plausible, and broadly consistent with the timeline we observe. The problem, identified in multiple observational campaigns and now deepened by JWST, is that the required number of ionizing photons from known stellar populations falls somewhat short of what the timeline demands. The reionization schedule, the rate at which the neutral fraction of the early universe dropped from 100% to essentially zero, requires more photons than the observed population of early star-forming galaxies can plausibly produce, unless the escape fraction of ionizing photons from those galaxies is very high, much higher than measured in similar systems. Something is either missing from the source budget, or the escape fractions are being systematically underestimated. At the little red dots, heavily obscured active galactic nuclei, accreting at near Eddington rates, produce copious amounts of ionizing photons from the accretion disk. Under normal circumstances, the circumstances of a typical quasar surrounded by a dust torus, most of those photons are absorbed by the dust before escaping. But the LRDs are not surrounded by normal dust structures. Their cocoons are ionized gas, not dust, and ionized gas has a different photon budget than dust. Some theoretical models suggest that LRDs, if they are indeed the dominant black hole population in the early universe, may have contributed meaningfully, perhaps substantially, to the epoch of reionization, adding a previously invisible flux of ionizing photons to the photon budget at exactly the time the universe needed them most. Rinaldi's team has described this as blowing their minds. The phrasing is theatrical, but the underlying physics is genuine. For the entirety of the pre-JWST era, the reionization budget was calculated using sources we could see. We counted stars, we measured their ultraviolet output, we estimated escape fractions. The answer came up slightly short. Slightly short could mean measurement uncertainty, or slightly wrong models, or any number of minor adjustments. But if the little red dots, thousands of them, in the first billion years, each accreting at near Eddington rates and producing ionizing radiation from a gas cocoon structure that may allow significant photon escape, were contributing to reionization all along, then we were not slightly short. We were working from an incomplete census. The universe's most transformative epoch may have had a hidden engine that ran entirely in the infrared, entirely invisible to every instrument built before JWST, which raises a question that no one in the field would presently claim to be able to answer with confidence. If we missed the little red dots for the entire history of modern astronomy before December 2021, what else are we missing? Science earns its credibility precisely by refusing to settle questions prematurely. And the little red dots, for all the explanatory power of the cocoon model and the black hole star hypothesis, have not been quietly resolved. The field in 2025 and into 2026 is a landscape of competing interpretations, productive disagreement, and data rich enough to support multiple partially correct answers simultaneously. The nature of the little red dots is not a solved problem. It is a problem that has been illuminated, and illumination reveals complexity as reliably as it reveals truth. Start with the Nature paper itself. The Rusakov and Watson cocoon model. The finding that little red dots are young supermassive black holes with masses of 100,000 to 10 million solar masses, buried in dense ionized gas, accreting near the Eddington limit, is built on a sample of objects with the highest quality JWST spectra obtained to date. That sample is not enormous. The analysis of electron-scattered line profiles is technically demanding, requiring spectra with a signal-to-noise ratio that JWST can deliver for the brightest LRDs, but not yet for the faint majority of the population. The 341 confirmed LRDs catalogued as of 2025 represent only a fraction of the population visible in JWST's deep fields, and of those 341, the number with the spectroscopic quality needed to test the electron scattering hypothesis rigorously is measured in dozens, not hundreds. Dale Kashevsky of Colby College, one of the most prolific LRD observers, has maintained consistent caution throughout the debate. Kashevsky's own modelling suggests that some fraction of the little red dots are consistent with scattered light from a deeply obscured active galactic nucleus. Not electron scattering from a cocoon, but regular dust or gas scattering of AGN continuum photons that produces a blue ultraviolet spectral component while still yielding the characteristic V-shaped Balmer break. Under this model, which is in some respects less radical than the black hole star scenario, LRDs are unusual but not unprecedented. Deeply obscured active galactic nuclei in the early universe, seen through a dusty medium that reroutes their light into wavelengths JWST is sensitive to. Unusual but physically conservative. The challenge for Kashevsky's scattering model, and he would be the first to acknowledge this, is that it struggles with the cliff and with objects like the companion LRD, nicknamed MOM-BH1, which Rohan Naidu's group identified as a close analogue of the cliff at slightly higher redshift. For those objects, the sharpness of the Balmer break and the specific shape of the UV to optical continuum resist the scattering interpretation. In Ayoshi and Maialino, in a 2025 Astrophysical Journal Letters paper, demonstrated through detailed modelling that the Balmer break and absorption features of the sharpest LRD spectra favour a non-stellar origin, consistent with nebular emission from a dense gas cocoon dominating over any stellar component, rather than scattered AGN light. The two models agree on the black hole component. They disagree on the structure of the surrounding medium. Then there is the supermassive star hypothesis, which arrived in July 2025 in a paper by Devesh Nandal and Abraham Loeb of Harvard, published in the Astrophysical Journal. Nandal and Loeb proposed that at least some little red dots are not black holes at all, not yet. They are massive population 3 stars, the theorized first generation of stars to form in the universe, composed of pure hydrogen and helium with no metals, potentially reaching masses of 1 million solar masses or more, blazing with a luminosity that would outshine entire modern galaxies. Population 3 stars are predicted to be very massive, very hot, and very short-lived, lasting perhaps a few million years before their cores collapse. Nandal and Loeb's theoretical modelling showed that the spectral signature of a population 3 star in its final thousands of years of life, specifically the combination of a strong broad H-beta emission line, other Balmer lines in absorption, and the characteristic V-shaped Balmer break, match the observed LRD spectra with accuracy comparable to the black hole cocoon model. The population 3 hypothesis is an extraordinary idea. It would mean that some of the objects JWST has been staring at are, in a very direct sense, the first stars of the universe, objects whose existence was predicted 50 years ago and whose spectra were modelled theoretically, but had never been matched to an observed astronomical source. If Nandal and Loeb are correct for even a fraction of the LRD population, JWST has not merely found the infant stage of supermassive black holes, it has found the first generation of stellar objects directly, the population that preceded all subsequent stellar chemistry, all metal enrichment, all complex molecular formation, all planetary systems, and ultimately all biology. It would, without exaggeration, be the most direct observational connection ever established between the current universe and the moment of first star formation. The black hole star model and the population 3 model are not mutually exclusive. Nandal and Loeb explicitly hypothesized that population 3 stars of this mass would end their lives in a direct collapse. their cores imploding into black holes without a supernova explosion energetic enough to unbind the stellar envelope. The result, immediately after core collapse, would be a black hole enclosed within the residual gas envelope of the population 3 star, which is structurally precisely what Begelman, Naidu, and de Graaf's black hole star models describe. Population 3 stars may not be an alternative explanation for LRDs. They may be the progenitors of the black hole stars, the brief, brilliant phase that immediately precedes the formation of the gas-enshrouded young black hole. The morphological picture adds another layer of complexity. Pierluigi Rinaldi's team, analysing JWST imaging data in a paper published in October 2025 using the title Not Just a Dot, found that 30% of the 99 LRDs they analysed morphologically showed complex structure, multiple associated components, asymmetric profiles, or signatures consistent with recent galaxy interaction and merger events. This is not a population of uniformly pristine, isolated objects. Many of them appear to be forming and accreting in environments shaped by collisions, gas flows from nearby overdensities, and the kind of dynamical violence that characterises the early universe's densest regions. The LRD J107AGN at redshift 7.3 sits embedded in an overdensity of 8 nearby galaxies, a proto-cluster environment where the black hole galaxy coevolution process is happening in the most extreme possible context. Meanwhile, the question of what LRDs look like in the local universe, or its approximation, received an unexpected contribution in early 2025 when a team led by Rukyu Lin identified 7 V-shaped broadline green peak galaxies in a sample of 2,190 local compact objects from the Sloan Digital Sky Survey. Green pea galaxies are rare, compact, intensely star-forming objects in the nearby universe. The 7 identified by Lin's team showed the same V-shaped spectral energy distribution, the same broad emission lines, and the same evidence for overmassive black holes, relative to their host galaxies, that characterize the distant LRD population. If these green peas are local analogues of the high redshift LRDs, they offer an unprecedented opportunity. The distant LRDs are unresolvable in any current imaging system. The green peas can be studied with the full suite of current and future observational facilities: high-resolution radio imaging, optical interferometry, detailed X-ray searches at the spatial resolution needed to probe their innermost regions. And then there is the question raised by the Ruby survey's own most unexpected finding. Not the LRDs themselves, but the massive quiescent galaxies discovered in the same dataset at redshifts between 2 and 5. These are fully formed, star formation stopped, massive galaxies at a cosmic epoch when no such objects should exist in the numbers observed. 10 times more massive quiescent galaxies than LeCDM predicts. Their presence in the same survey as the LRDs suggests a broader pattern. The early universe assembled structure faster, more efficiently, and through mechanisms more varied than the standard model describes. The LRDs are not an isolated anomaly. They are a representative symptom of a larger failure of our models to capture the true pace of early cosmic evolution. This is where the credibility of the LRD story, the part that separates genuine scientific advance from overclaimed discovery, lies in the acknowledgement of what remains unknown. The Copenhagen model explains a great deal. The black hole star framework adds a structural and evolutionary dimension. The population 3 hypothesis opens a deeper possibility. But the field is not converged. Anna Christina Eilers of MIT, whose group has been watching the LRD literature accumulate since 2022, put it with characteristic precision in late 2025. I don't think there is any consensus yet, and even if there are theories we like, there are a million open questions. One of the most important open questions is whether all little red dots are the same class of object. Karina Caputi of the University of Groningen, whose morphological and photometric analyses have been among the most careful in the field, has argued explicitly that different LRDs may have fundamentally different natures, some powered by black hole accretion, some by extreme star formation events, some by combinations of both, and that the quest for a single unified explanation may itself be a category error. The V-shaped Balmer break may be a spectral signature achievable through multiple physical pathways, and the similarity of LRD spectra may reflect not a single object class, but a common observational selection effect. JWST is uniquely good at finding red, compact, hydrogen-rich objects in the early universe, and there may be more than one way to be red, compact and hydrogen-rich. The question of the escape fraction of ionizing photons from LRDs remains observationally unconstrained. The contribution of LRDs to reionization, potentially significant, possibly dominant in certain redshift bins, cannot be calculated until the photon budget of the cocoon model is better characterized. Does the dense ionized gas surrounding a young black hole absorb all of the ionizing radiation, reprocessing it into optical light? Or does it allow some fraction to escape into the intergalactic medium? The answer changes the reionization budget by a number that may be modest or may be revolutionary. The disappearance of LRDs at 1.5 billion years after the Big Bang is also unexplained in quantitative detail. The qualitative story is coherent. Black hole stars shed their envelopes. As the central black hole grows massive enough to drive powerful outflows, the gas cocoon disperses, the object transitions from an LRD into a more conventional quasar or active galactic nucleus, and the population as a discrete photometric class vanishes. But the transition timescale, the mass at which the transition occurs, the mechanism of envelope dispersal, these are model parameters, not observations. Testing them requires either catching an LRD in the act of transition, something no JWST program has yet definitively accomplished, or finding a population of objects at intermediate redshift that represents the bridge between the LRD phase and the classic quasar phase. Naidu and his MIT collaborators are working on exactly this problem. His stated goal, producing a Hertzsprung-Russell-like diagram for black hole stars, mapping their evolutionary stages against measurable spectral parameters, requires characterizing dozens of LRDs with the kind of precision that only JWST's highest resolution NIR spec configurations can provide, and possibly only the upcoming generation of extremely large ground-based telescopes with their 30 to 40 metre primary mirrors. The extremely large telescope, the Giant Magellan Telescope and the 30-metre telescope, all currently under construction or in advanced development, will have the sensitivity and resolution to probe LRD spectra at signal-to-noise ratios that would settle several of the current debates definitively. That data, however, is years away. In the meantime, the field moves forward with the particular velocity that characterises JWST science in 2025 and 2026. Dozens of research groups submitting observational proposals for every available telescope, preprints appearing faster than peer reviewers can read them, and a community of cosmologists who freely acknowledge, with something between exhilaration and disorientation, that their foundational model of the universe's early structure is being revised in real time by a machine that was built precisely to find what they did not know to look for, which is, in the end, the highest compliment that can be paid to any scientific instrument. The question of what the little red dots ultimately tell us about the universe is one that will be answered over years and decades, not months. But the direction of travel is already clear enough to say something meaningful about where the field is heading, and what the implications are for the way we understand cosmic history. The most immediate frontier is the CAPAS program, Cosmic Ancient and Powerful Extragalactic Sources, a JWST survey that has already delivered the object CAPAS LRD-Z9 at redshift 9.288, confirmed in August 2025 as the highest redshift active galactic nucleus yet identified in a universe 540 million years old. CAPAS is one of several large JWST survey programs now specifically designed to push LRD observations toward the highest possible redshifts to find these objects as close to their birth moment as current technology permits. Every confirmed LRD at a new record redshift tightens the constraint on the formation pathway. If an accreting black hole of 100,000 solar masses already exists 500 million years after the Big Bang, the seed event that created it must have occurred within the universe's first few hundred million years. In a regime where population 3 star formation and direct collapse are the only plausible candidates, and where JWST, combined with the Roman Space Telescope launching in 2027, may begin to resolve which one actually dominates. The Roman Space Telescope, formerly known as the Wide Field Infrared Survey Telescope, will survey areas of sky hundreds of times larger than any individual JWST deep field in the same near-infrared wavelengths where LRDs are detected. Where JWST finds dozens of LRDs per field, Roman will find thousands, potentially tens of thousands per survey tile. The statistical power of a Roman LRD catalogue would allow, for the first time, the kind of demographic analysis needed to map the LRD mass function, the distribution of black hole masses across the population, with the precision necessary to distinguish between direct collapse formation, stellar collapse formation, and population 3 progenitor scenarios. Fabio Pacucci's dark matter halo spin model, for instance, makes specific predictions about the LRD number density as a function of halo mass and spin that a Roman survey could test directly. The ground-based extremely large telescopes add a different capability. JWST's NIRSpec instrument obtains spectra with extraordinary sensitivity, but its spectral resolution, its ability to distinguish fine detail in the velocity structure of emission lines, is limited at the line widths characteristic of LRDs. The ELT's Harmony instrument and the GMT's G-clef spectrograph will operate at spectral resolutions 10 to 20 times higher, making it possible to characterize the intrinsic line widths of LRDs. The narrow cores buried within the electron-scattered broad profiles, with the precision needed to measure black hole masses to better than a factor of 2. Currently, the mass uncertainty for individual LRDs spans an order of magnitude. Reducing that uncertainty is not a cosmetic improvement. It is the difference between distinguishing between population 3 progenitors, direct collapse seeds, and ordinary stellar black hole remnants, the 3 formation scenarios with the most different implications for LECDM. The reionization question will be addressed through a combination of JWST and the Square Kilometre Array, the radio observatory currently under construction across Australia and South Africa, with a planned operational date of 2028. The SKA is specifically designed to map the 21 cm emission from neutral hydrogen in the epoch of reionization, the signal that traces, bubble by bubble, the ionization of the early universe's hydrogen fog. Cross-correlating SKA's reionization maps with JWST LRD positions will reveal whether the LRDs sit preferentially at the centers of ionization bubbles, the signature expected if they are, themselves, significant sources of ionizing photons. If they do, the reionization budget will need to be recalculated from the ground up to include the contribution of obscured black holes, alongside the stellar sources that have dominated the accounting until now. There is another implication worth dwelling on, one that belongs less to the observational program and more to the foundational architecture of cosmological theory. The overmassive black holes in early galaxies, the reversed galaxy black hole mass ratios seen in objects like Virgil and Kuiper's LRDZ9, and the apparent efficiency of mass assembly in the early universe collectively point toward a need for what theorists call a revised feedback prescription in LECDM simulations. Feedback, the process by which energy output from stars and black holes regulates further star formation and black hole growth, is one of the least well-constrained elements of galaxy formation models. Current simulations tune their feedback parameters to match the observed properties of galaxies in the nearby universe. If LRDs represent a class of objects that grew rapidly through a near feedback-free early phase, protected by their dense gas cocoons from the winds and radiation that normally regulate accretion, then the feedback recipes used in cosmological simulations are missing a phase. Missing a phase means missing a chapter, and missing a chapter in the formation history of galaxies means that every simulation of cosmic structure built to date, including the state-of-the-art Illustris TNG and EA Glee simulations that represent the gold standard of the field, contains a systematic error in their treatment of the earliest epoch of black hole growth. Not a catastrophic error, not a collapse of the entire modelling enterprise, but a real measurable discrepancy between simulation and observation that will require new physics, or at minimum new parameter choices, to close. The search for local analogues of LRDs, the 7 green P galaxies identified by Lynn's team, the radio-detected nearby LRD from December 2024, the broader program of searching archival Sloan Digital Sky Survey data for objects with V-shaped spectral energy distributions and overmassive black holes, represents perhaps the most tractable near-term path to the kind of high-resolution characterization that distant LRDs preclude. A local analogue studied with the Chandra X-ray Observatory at the resolution needed to separate the nuclear point source from the host galaxy, with the Very Long Baseline Array at the resolution needed to image the inner jet structure, and with the Atacama Large Millimeter Array at the sensitivity needed to detect or rule out cold gas reservoirs. Such a dataset would provide the physical ground truth against which every model of the distant LRD population is ultimately tested. And beneath all of this, beneath the spectral models, the formation pathways, the reionization budgets, the dark matter halo spin distributions, the observational programs of the next decade, there is a question that does not yet have even the outline of an answer. If some little red dots are population 3 stars in their final thousands of years of existence, as Nandel and Loeb proposed, then JWST may already have in its data a direct observation of the first stellar generation, the objects that produced every atom of carbon, oxygen, nitrogen, and every other metal heavier than hydrogen and helium that makes up planets, atmospheres, and ultimately life. We have been looking for population 3 stars since the theoretical case for them was made in the 1970s. We have never unambiguously detected one, but the JWST archive now contains hundreds of LRD spectra. If population 3 stars are there, hidden in the subset of LRDs, whose spectral breaks and emission line profiles are most consistent with the Nandel and Loeb models, they will be found, not in a future observation, but in data that already exists, sitting in a server in Baltimore, waiting for the right analysis to extract them. That is the precise nature of what JWST has delivered. Not just new observations of distant objects, but a data archive of sufficient quality that discoveries are still being made from first light datasets acquired in 2022 and 2023. Every large JWST survey program adds to that archive. Every new spectroscopic analysis technique, every improvement in stellar population models, every refinement of the electron scattering line profile fitting procedure reaches back into the archive and pulls out new results. The James Webb Space Telescope is not just a telescope. It is a time machine with a library built in. And the little red dots, those impossible, maddening, paradigm-disrupting specks that showed up in the very first images and refused to be explained, are the library's most important collection. There is a moment, somewhere between 400 million and 600 million years after the Big Bang, when the universe made its first complicated decisions. Gas fell into the deepest wells of dark matter. Something, whether a primordial star of unimaginable mass, or a cloud of gas collapsing directly into a gravitational singularity, or some intermediate structure we are only beginning to name, ignited, not with the quiet, orderly fusion of a normal star, with something more violent, more concentrated, more energetically dense. A black hole, young and hungry, wrapping itself in a cocoon of its own making, glowing crimson through the gas, small by cosmic standards, 100,000 times the mass of the Sun, or 1,000,000 or 10,000,000, impossibly large by human reckoning, and yet modest by the standards of what it would one day become. It lasted a few million years, and then the outflows won. The cocoon dispersed, the red faded. The object that remained was a naked black hole in an infant galaxy, ready to grow, at a slightly more measured pace, toward the billions of solar masses that would eventually anchor the mature galaxies of the present universe. Every galaxy, including ours. This is, when you sit with it long enough, a genuinely extraordinary thing to contemplate. The Milky Way, the galaxy in whose outer spiral arm one particular star ignited 4.5 billion years ago, in whose habitable zone a rocky planet assembled, on whose surface chemistry eventually stumbled into replication, and then awareness, may owe its existence to one of those tiny red dots. The supermassive black hole at the centre of the Milky Way, Sagittarius A star, 4 million solar masses of compressed spacetime, was once a young black hole inside a gas cocoon. It blazed crimson in the cosmic dawn. Had JWST existed 13 billion years ago and been pointed at the right patch of sky, it would have appeared as a little red dot. We are, in a very real sense, the descendants of those objects. What strikes me most about this story, and I have spent a long time sitting with it, is not the science, extraordinary as it is. It is the fact that the answer was waiting in the first images the telescope ever took. The little red dots appeared in July 2022 in the telescope's first public data release, seen by thousands of astronomers simultaneously. They did not require a new observation. They did not require a new instrument. They required, above all else, the willingness to stare at something inexplicable long enough to stop trying to fit it into existing categories and start asking what it actually was. Science sometimes works this way. The data arrives before the understanding. The universe shows you something and then waits, with the patience of cosmological time, for you to develop the language to describe it. The little red dots waited 3 years. Some questions wait longer, some have been waiting since we first looked up. We are still at the beginning of the LRD story. The Nature paper from Copenhagen is not the final word. It is the opening statement of a much longer argument that will play out over the lifetimes of the next generation of telescopes. The Roman Space Telescope will find thousands more. The extremely large telescope will resolve their line profiles to a precision that will distinguish between formation scenarios as cleanly as a fingerprint. The square kilometre array will map the reionization signature and tell us, finally, whether those small red fires in the cosmic dawn lit the universe or merely watched it burn. And somewhere in the JWST archive, in data already collected, already downloaded, already sitting on a hard drive, there may be a spectrum that matches, feature by feature, the theoretical prediction for a population 3 star in its last few thousand years of life. The first star, the original star, the one whose core collapse seeded everything that followed. Science doesn't always give us endings. Sometimes it gives us horizons. The little red dots are not a solved mystery. They are a solved first layer, beneath which the real mystery now begins to glow. We have named the cocoon. We have measured the black hole inside it. We have glimpsed, in the sharpest spectra yet obtained by the most powerful telescope ever built, the outline of a phase of cosmic history that predates every star in every galaxy we have ever studied. What we have not yet seen is what came before even that. The answer belongs to whoever looks next.